Hey everybody, if you don't know me, my name is Connor Bison. I'm Supplemental Instruction Leader at Georgia Southern University. This is my studio. All the magic happens here. But this video is going to be going over the practice final I posted on Folio. I'm going to be going over a lot of other things that are not on the practice final to prepare you guys for the actual final. Again, the ACS standardized final that 1152 has to take is over 1151 and 1152. So it's a lot to cover, long video, but please watch all of it. It will be very beneficial. I work pretty much everything. It took a long time, but anyway, if you guys make it all the way through and you do well in your final and everything, I wish you guys a wonderful summer. Best luck on all your other finals, and have a great summer. Alright, let's get into it. Alright, what's up everybody? I have here the review final that I made. I talked to a bunch of teachers about it. They seem to think it's pretty good. Obviously, it can't cover everything, so the things I couldn't get too crazily was some structure stuff that's simple stuff. We've done it in class 10 million times, but this is stuff that's like, you know, you might need a refresher on. So, I guess let's just go ahead and dive into it. Hopefully you can see my actual test. I'll be reading along with it. And then over here I have my paper. I'll do every problem. I'll work it out. So number one, just simple conversion. 0.274 liters is equal to how many centimeters cubed? The only trick in this one, which your chem teacher may or may not have taught you, is that, and you'll need to know this, 1 milliliter is equal to 1 centimeter cubed, right? So now that we know that, we need to figure out how many milliliters 0.274 liters is. So 0.274 liters, 1, and then you have 1,000 milliliters per 1 liter equals out to be 274 milliliters. Okay, so we have 274 milliliters, and remember it's just same centimeters cubed and milliliters are the exact same thing. So your final answer is 274 milliliters, which is answer choice B. So I'll go ahead and circle that. So moving on to the next one. Chicken noodle soup is an example. Chicken noodle soup is an example of it should be A, not and, but whatever. Homogeneous mixture, heterogeneous mixture, an element or a pure substance. Okay, the main thing in this question, it's asking about homogeneous versus heterogeneous. So the difference between the two, in a homogeneous mixture, if I took any part of it from any portion of it, it would be the same, no matter what. It's like if I had a glass of water, if I take a drop of water out from the middle, it's going to be the same as if I take a drop of water out from the side. But with chicken noodle soup, if I take something from the middle, I might get some noodles, I might get some chicken. If I go from the sides, I could get something else, I don't know. It's not uniform throughout. Homogeneous is uniform throughout, exactly the same, any place you look at it. Heterogeneous, not so much. It's different. So an element, you guys should know what that is. It's furthest thing broken down. Pure substance just means it's composed element stuff. I won't really worry about that. So answer is B, heterogeneous mixture. Alright, 17.4 milligrams of an unknown substance occupies this many microliters. What is the density of the unknown in grams per milliliter? Okay, this is a more advanced conversion. I'd still expect to see it. It's a density problem. So remember, density, which I'll just represent as a capital D, is equal to mass over volume. And this time they want it in particular in grams per milliliter. So we'll just work bit by bit, right? So we have 17.4 milligrams of an unknown substance. It doesn't matter what it is right now. And we need to convert that to grams. So we go 17.4 milligrams over 1. So let me extend this out some. That way it just looks a little bit cleaner. So now there's 1,000 milligrams per 1 gram. So milligrams will cancel out there. That will give us our number of grams, which should be 0.0174 grams. Alright, so now we got to go over milliliters. So we have 952 microliters. Now, do you guys remember what micro was? Hopefully you do. It's 10 to the negative 6th. You guys couldn't remember it. So, anywho, a little trick we can do is, since it's 10 to the negative 6, milliliters 10 to the negative 3, you can just scoot everything over 3 places if you want to do that. If not, you can do the same like little tunnel thing I've been doing, but we'll scoot it over 1, 2, 3, 0.952 milliliters. Okay, so now it's grams per milliliter, so 0.0174 grams divided by 0.952 milliliters. And let me see what I come out to get. You're not allowed to use your phone, so do as I say, not as I do. Let me pull up a calculator. This is the old iPhone 4. She's holding strong for me. But okay, so we got 0.0174 divided by 0.952. I get a density of 0.0183. That's my density. And that is one of the answers. That's answer choice D. So we'll go ahead and circle that. Alright. So now we have another one here. Sorry, my Facebook's like popping up. Anyway, we got another one here that's a patient's temperature is 38.5 degrees Celsius. What is their temperature in Fahrenheit? So, give me 2 seconds. My computer's doing something really weird. Okay, anyway. So, if we want to convert things to Fahrenheit, this is the equation for it. We have degrees Fahrenheit is equal to 1.8 times degrees Celsius plus 32. So, they gave us a degree Celsius of 38.5, so we're going to go 1.8 times 38.5, was that it? Yeah. And we get 69.3 plus 32. We get 101.3. So degrees Fahrenheit equals 101.3 degrees Fahrenheit. Okay. So, hopefully that makes sense for you. Again, here's the equation. It's stuff you've done a long time ago. I wouldn't sweat it too much. So, 101.3. So, they have a pretty bad fever, but nothing crazy. Next one, let's see. It's just simple definition stuff. Just checking stuff. I've seen this question pop up in every ACS thing ever, so figured why not continue the trend and put it in this practice exam. So it's the blank is the smallest building block of matter. It's the atom. So just remember, atoms compose, or molecules are composed of atoms. Just, yeah. So atoms. So yeah. 5C. I don't really need to explain that one that much. Next one, I might have to explain to a little bit more. This one's a little bit more complicated. It's using atomic mass number, proton numbers, which we'll find out and stuff. So 6, an unknown element is observed to have a mass number of 19, have 9 electrons, that's what that E with the minus sign is, and has a neutral overall charge. What element is being observed? Okay, so there's a couple ways we can go about this. I know you guys did this in 151, so it's going to be a little bit old in your mind, I guess. It's just a long time. But there's a couple ways you can go about it. You can look at atomic mass number, which is 19. You can look in the periodic table and just look for something with a mass of pretty much 19, which it says is fluorine. So that's our first guess, but we'll see. So fluorine. And then it says it has 9 electrons and has a neutral overall charge. Whenever they specify that, neutral overall charge, it means protons is the same as your number of electrons. So if we have 9 electrons, we're going to have 9 protons to counter it out. So 9 protons, we can look for atomic number 9 up there, which is fluorine. 9 protons is fluorine. So what element is being observed? Fluorine. So answer choice C. Okay. What is the most significant intermolecular force in HF? Okay. So there's a couple different molecular intermolecular forces, and I'll put them here. We have London dispersion. I'll just write it as London. Let me do that so you can see it. So London dispersion. We have dipole-dipole. We have hydrogen bonding, so I'll just put H bonding. And then we have ionic. Okay, they get stronger going down this list, so hopefully you guys can see that. And then London dispersion, it's in freaking everything. Every compound has London dispersion. Some people say ionic. Technically, it doesn't have it, but yeah. Anywho, dipole-dipole, anything polar. So anything polar. H bonding, you're going to look for a hydrogen that is bound to a nitrogen, oxygen, or fluorine. So you'll be looking for that. Ionic, you're going to look for metal and a non-metal. Okay, and again, they get stronger, the forces going here. So when we look at HF, well, I guess I need to explain polarity first in case some of you guys don't understand polarity, right? So polarity, the best way that I've taught it and that I learned it was as, think of it like tug of war, right? So if we have A and B, 2 people playing tug of war, right? A is pulling his way with like 15 pounds of force. He's a wimp. B is pulling his direction with, let's say, like 200 pounds of force. Then this tug of rope, the whole thing is going to shift towards B, correct? It just makes sense. B's pulling stronger. Well, polarity is basically the exact same thing, except instead of pounds, we're talking about electronegativity. So the only thing you really need to know about that is things are more electronegative the closer they are to the top right-hand corner of the periodic table. So things like fluorine, chlorine, oxygen, sulfur, they're pretty strong. They pull pretty hard. So, and hydrogens, even though some periodic tables have it listed on the top right, it's not really. It's just it's the far left, so it's the least strong. So again, that's polar, right? If it shifts in one direction, one's stronger than the other. If it's non-polar, they pull with the exact same amount of force. So I'll give you an example. A polar example would be actually the one we're looking at, HF. It's a hydrogen bound to a fluorine. So fluorine, because you can see it's top right hand corner on the periodic table, besides the noble gases, ignore them, it pulls freaking hard, right? It's going to pull really tough. Hydrogen is a freaking wimp. It's not going to pull very hard at all. It's going to be that little thing right there. Like, pretty much nothing. So, it's going to shift in one direction towards fluorine, which makes it a polar molecule. So, something non-polar would be something like this. CH4, which is methane. Even though, yeah, there's a ton of different things. If you look, we have a central atom, 4 people playing tug of war, right? And they're all pulling with the exact same strength because they're all hydrogens, right? So it just cancels out. You'll see something like a CCl4, it's the same thing, non-polar. But anyway, so looking at HF, which is what we needed in this problem, right? HF, does it have London? Yeah, it's got London. Everything's got London. Dipole, dipole, anything that's polar. And we're talking about it. It is polar. But remember, it also has hydrogen bonding because it's a hydrogen bound to a nitrogen, oxygen, or fluorine. So it's a hydrogen bound to a fluorine, so it has hydrogen bonding. It definitely doesn't have ionics, not a metal and non-metal. But the most significant force, remember, it gets stronger going down this way, is hydrogen bonding. So that would be answer choice C. So I'll be right back. I'm gonna grab a drink. Okay, sorry, I was pretty thirsty. Anywho, on to number 8. What is the molecular shape of BCl3? So this one, I mean, I don't know the best way to tell you besides like learn it. You can look up something called a VSEPR chart, which is VSEPR, if you want to memorize some of them. But BCl3 is trigonal planar, just so you guys know. So, yeah. Anywho, I'll go ahead and mark it. And then something like tetrahedral, that's when you see something that's like, what would be a good one? CCl4, that's tetrahedral. You'll run into a couple other things, but in this case, what we're looking at is trigonal planar. Again, look up VSEPR chart just to familiarize yourself with some of the stuff, but it's pretty easy overall. You just memorize a couple of them, no problem. Okay. Number 9, how many molecules are there in 4.3 grams of methane? Okay. So this one, it's a little bit weird because we're looking for molecules, right? So there's actually a couple steps we got to do first. So first thing we got to do to find molecules, we have to find moles first. So we have 4.3 grams. So right there, right here. 4.3 grams of CH4, so methane. Okay, so to get moles, we're going to divide it by its molar mass, right? So 1 mole divided by 16, that's how much all those components combined are. Carbon plus 4 hydrogens, 16 grams. So we'll do that and it will give us a number of grams, which let's see, so 4.3 divided by 16, we have, or not grams, give us number of moles, 0.26875. That's way too many. You can round it off somewhere, moles. Okay, so now it says how many molecules. Now remember, to go from moles to molecules, you're going to take your number of moles and you're going to times it by Avogadro's number, right? Which is 6.022 times 10 to the 23rd. That's Avogadro's number. So I think that's actually being given to you. I was talking to Dr. Kuchera about it, and I'm pretty sure they're giving that to you, the 6.022 times 10 to the 23rd. So I would expect a problem on there doing this. But 0.26875 times 6.022. Alright, I get 1.62 pretty much times 10 to the 23rd molecules. Nice. So 1.62 times 10 to the 23rd, which is an answer choice, which is answer choice A. Sweet. Moving on to the next one. What is the name of the following compound? SF6. You might want to look up videos. This is a side note. You might want to look up videos of this once we go over the name, because it's really funny stuff. But so since it's two nonmetals, right? Let me flip this piece of paper. Since it's two nonmetals, we go by the first one. So sulfur, that's what it is. It's not sulfate. Sulfate's a polyatomic ion. So yeah, not that, but sulfur. So sulfur, I'll write that down. And then since it's two nonmetals, you have to specify how many of the fluorines there are, which there's 6. So you use the prefix hexafluoride. So the name of this is sulfur hexafluoride. If you pull up videos of it, it's really funny. If you breathe it in, it's basically the opposite of helium. It makes your voice super deep. But I think technically it's a greenhouse gas, so people don't like it very much, but I think it's pretty funny. So sulfur hexafluoride, answer choice C. Okay. Number 11, what is the correct IUPAC name for the following organic structure? I'll move this up a little bit so y'all can see it. If not, hopefully you're following along on the folio test. So it's this ring right here with 2 methyl groups. So normally, I know some of you guys would think, oh, it's cyclohexane because it's a 6-membered ring. But actually, because it has these double bonds in there, that's a benzene. This is a benzene ring. So since it's 2 of these methyl groups, you have to give it the lowest number of substituents pretty much. So we'd count and go 1, 2. And so the name of it would be 1, 2 dash dimethyl, di because there's 2, benzene. That'd be the answer to that one. And that's answer choice A. Okay, we're about 1/5 of the way done, so making good time here. Alright, moving on to number 12. What is the correct IUPAC name for the following organic structure? Okay, these are really tricky. These used to trick me in organic. So take your time with this. First thing we want to do is we want to look for the longest carbon chain. So let's start counting some of these and see what we can get. Sorry if my hand's blocking the way, but unfortunately there's nothing we can do. So 1, 2, 3, 4, 5, 6, 7. It's 7 long when I go that way. 1, 2, 3, 4, 5, 6 if I go that way. And it's going to be the same on the other side, 6. So 7, it does go this way. So 7, right? So what does that make it? That makes it a heptane. So heptane is going to be the final bit. So we can already narrow it down to 2 answer choices, which is B and C. So that's nice. So you can do that on the test as well, because they'll put hexanes and stuff like that on there. But so we can see we've narrowed it down to B and C, right? So now we have to count these substituents, right? So if we go 1, 2, 3, 4, our first group would be on the 4th group, and it's an ethyl, and then it'd be 5-methyl heptane, which that's kind of weird. Numbers are really high. Let's see if we go the other way. 1, 2, 3. So if we start there, we get our first added group, which is our methyl group, at 3, which is lower than doing the other way, and that's what you have to do to get the correct answer. So it's going to be 1, 2, 3, so a methyl group at number 3, and then at number 4 there'll be an ethyl. So you end up with 4-ethyl dash 3-methyl heptane. So that's answer choice B. Alright. Number 13, stereoisomers that are non-superimposable images are called what? So, hang on, I got something popping up. I did probably like close stuff. That's weird. I just had like all this random stuff pop up and it was like, you know, where did this come from? Anyway, so 13, back to where it was. Stereoisomers that are non-superimposable mirror images are called, that's enantiomers. That's just like the definition of an enantiomer. On the test, you'll probably have to recognize it, but I mean, if you know the definition, you should be able to reason out in your head and be able to get it. So structural isomers, it's the same formula, but they're connected different. Conformational isomers, it's like same, they connect the same, but their arrangements are a little bit different. And then cis-trans, you guys know cis-trans stuff. So, again, the answer is D. This is a tricky question, the next one. An example of an endothermic reaction is what? A candle flame, combustion, freezing water, or melting ice cubes. So, we got to think about this one. So, an exothermic reaction is something giving off heat, right? Giving off heat to the environment. So, an endothermic reaction is absorbing heat to itself, right? So if you look through all these, we have a candle flame. That's giving off heat to the environment. So that's exothermic. So I'll go ahead and cross that one out. Combustion. So like an explosion. Yeah, that's going to give off heat to the environment. No problem. Then we have freezing water and melting ice cubes. Freezing water actually is, you wouldn't think of this, and this is why they put this in a lot of ACS tests, and it trips people up every single time. Freezing water is actually exothermic because it's not absorbing heat, it's technically giving off heat to the environment so it can become colder to freeze. While melting an ice cube, it's bringing in heat to itself and then, you know, melting as a result. So freezing water is exothermic. Again, that's because as it's freezing, it's getting colder. For it to get colder, it has to give off its heat. While melting ice cubes, it's absorbing heat directly to melt itself. So answer choice D is correct here. 15 is very similar to it. A particular reaction has a negative delta G value. What is true of this reaction? So exergonic and exothermic are, I mean, pretty much the same thing. Endergonic and endothermic is pretty much the same thing as well. So if it has a negative delta G value, it means it's giving off heat to the environment. So we can look through endergonic, so that would be taking in heat. That's definitely not it. C, the reaction absorbs energy. That's not true. Is non-spontaneous. If it has a negative delta G value, it is spontaneous. That's just something you gotta know. But B is the reaction is exergonic, so exothermic pretty much, which is true. So B is the correct answer. Okay, the following reaction is an example of what type of reaction? And we have 2 NaCl plus H2 gas yields 2 hydrochloric acid plus sodium. And your answer choices are a synthesis reaction, a decomposition reaction, single exchange reaction, or a double exchange reaction. So this right here, it's actually just a single exchange reaction because you can see just one thing gets swapped out here. The sodium and the hydrogen get swapped, and That's really it. So it's a single exchange reaction. Decomposition would be if you had something that was like AB breaking down into A plus B. That's decomposition. Synthesis is that backwards. So A plus B yields AB. And then double exchange would be if you had AB plus CD yields AD plus BC, where both things swap out. But anyway, yeah, single exchange reaction. Hopefully that makes sense to everybody. It's not bad. But alright, on to 17. Which of the following compounds would have the highest boiling point? Okay, let me go back to the other page here. So, back on the other page, you saw how we were talking about London dispersion, dipole-dipole, hydrogen bonding, and ionic, right? So, that's the strength of their bonding increases going down this list, right? So, essentially, the stronger the bonding, the harder it is for it to boil. So, it has a higher boiling point. So, which of the following compounds would have the highest boiling point? We have to look at all of them and see what's their strongest intermolecular force. So, HCl, what's that? Well, it's polar. So, dipole-dipole. Dipole-dipole. Okay. CH4, that's nonpolar, so it's just got London. That's pretty suckish. HF, hydrogen bonding. So that's pretty nice. And then barium chloride. Yeah, this is... Oh, actually, mistype. I just saw it. It should be BaCl2, not BaCl. I'll probably make sure the folio one has that fixed. But yeah, it should be BaCl2. But regardless, it has ionic, right? Ionic. And remember, ionic's one of the strongest intermolecular forces, right? So it does not want to come apart. It wants to stay together. So its boiling point is going to be very high compared to the rest of them. So you would expect it to have the highest boiling point. So D is the right answer here. So, alright, on to 18. Which compound would most likely dissolve in butane? This is using a rule. You guys, I think you've seen it before. If not, it's most likely going to be on the test. It's this, quote, golden rule, which is that like dissolves like. I'll write that on here. Like dissolves like. And what I mean by that is polar dissolves polar, nonpolar dissolves nonpolar. So when we look at this, we have butane, right? So hopefully you guys know what butane looks like. So if you do, it's nonpolar. So it's 1, 2, 3, 4. 1, 2, 3, 4. That's what butane looks like, that structure right there. So it's just carbons and hydrogens all over the place. That's it. It's nonpolar. So we're looking for something that is nonpolar on here. So we have water. Water's polar. Hopefully you guys knew that. It's even called the universal solvent, if you ever run into that. Ethanol is definitely polar. If you guys don't know what that looks like, it's bam, bam, and then you had, so 1 carbon, 2 carbon, and then you had an oxygen with a hydrogen. That's ethanol. So that's polar. Methanol is pretty much the same thing, just that. So that's polar. Methane is not. It's CH4. This. Yeah, there we go. I'll just do this already big. So that's methane. So nonpolar and nonpolar, like dissolves like. Methane is the correct answer, which is answer choice B. Okay. On to the next one. We have a constant amount of helium gas. So that's already a pretty nice giveaway of what we gotta do here. At a constant pressure, that's the other giveaway, occupies 2.1 liters at 6.9 degrees Celsius. The gas is heated to 35.9 degrees Celsius what volume does the gas now occupy? Okay, hopefully you guys remember this. I think you're given this equation as well, or at least that's what Dr. Kuchera was saying. This is Charles' law, which is V initial over temperature initial is equal to V final over temperature final, right? So that's the equation for Charles' law. So now we start plugging and chugging, right? So it occupies 2.1 liters. So that's VI. And that's in a temperature of 6.9 degrees Celsius. But we can't put 6.9 degrees Celsius in. Remember, whenever you're dealing with gases, you have to deal with Kelvin. So to get Kelvin, it's degrees Celsius plus 273.15. So when we do this little thing right here, it's going to be, what was that? 6.9 plus 273.15. So that's going to be 280.05 Kelvin. Right? Is equal to V final, which we don't know, over temperature final, which they said it's 35.9 degrees Celsius. So remember, we got to convert that to Kelvin though. So 35.9 plus 273.15, and we get 309.05. Alright, so now we have to times both sides by this value right here. So we'll have 2.1 times 309.05 divided by 280.05. And let's see what that comes out to. 2.1, yeah. Divided by 280. You get a volume final that's equal to, you guys can see it for yourself, 2.32 pretty much liters. And pretty much, give or take. If you guys have answers that are like 0.01 off, it's just rounding somewhere, just take it. Even though mine would round fine to it, but anyway, that's answer choice B. Got a lot of B's and D's on this page. So 2.32 liters would be what it now occupies. So that's Charles' law again. So remember, you'll probably have to go over Charles' law and Boyle's law. Those are probably the two main ones that y'all have to go over. But 19 is a constant amount of helium gas. Oh wait, we just did 19. Yeah, I'm talking about 20 now. 20, an ionic compound that completely dissociates in water into its original ions, is a or an what? Okay, there's two things that they might be referring to here. A strong acid or a strong base completely dissociates in water. And so let's take, but there's also electrolytes. If it's a strong electrolyte, it would dissociate completely. So let's take, we have strong electrolyte, okay. A non-electrolyte, that would be if it didn't dissociate at all. A weak acid, weak acids partially dissociate in solution, they don't fully dissociate. And a weak electrolyte is a weak acid pretty much. A strong electrolyte is pretty much a strong acid, just so you guys know. So if it's an ionic compound that completely dissociates in water into its original ions, it's a strong electrolyte. So 20 is A. Let's go ahead and circle that. Okay, find the concentration in molarity of a 0.45 liter solution that contains 16.34 grams of hydrochloric acid. Okay, so first we got to talk about what molarity is. Hopefully you guys remember it. Molarity is equal to moles solute per liter solution. Okay, so we'll start plugging stuff in here. So liters solution, we got that. 0.45. I'll put 0.45, this little equal sign. That's not the answer, but it's just that little bit. So then this guy up here, moles solute. Do we have moles? No. But we do know we have 16.34 grams of HCl, which is hydrochloric acid. Hopefully you guys knew that. Oh, sorry, I got a text from a friend. But anyway, right, so we need to find how many moles that is. So the weight of HCl, let me look at my periodic table up here. 36.45. So 36.45, I'll just write that down really quick. Okay. So that's 36.45. So now we have 16.34 grams, because we want to convert to moles, right? I'll write it out every step. So now it's 36.45 grams per 1 mole. Now it'll give me how many moles it is. So let me take a peek really quick. So 16.34 divided by 36.45. We get about 0.448. About 0.448. So again, now we're just going to do moles solute, which is 0.448, divided by liters of solution, which is 0.45. So 0.448 divided by 0.45. I can tell you without even using a calculator, it's going to be like essentially 1. I mean, 0.448 divided by 0.45. Yeah, it's like 0.99555 forever. So 1 molar, which that's answer choice C. Alright, hey everybody. So I'm back. Sorry, there was some problem. The thing just cut off earlier. But anyway, so we're on number 22. So 5.2 liters of dichloromethane, which is a solvent we use in research a lot, is added to 2,451 milliliters of 6 molar HCl. What is the concentration of the resulting solution? Alright, this is just a simple, sorry, let me scoot this down some. This is a simple dilution problem. So this is the formula you use. C1V1 equals C2V2. The C's are just concentrations, V's being volume. You guys might have seen M1V1 equals M2V2. It's the same thing. So first then, we have 6 molar, so that would be our C1, times a volume, I'll just go ahead and convert it to liters, 2.451 liters is equal to C2 times V2, which is the 2.451 plus 5.2, so that's going to be 7.651, I think. Yeah. Okay. So now you can see we're just going to divide both sides by 7.651. So let me pull up the calculator. 6 times 2.451 divided by 7.651, and I get 1.922 molar, and that's answer choice D for y'all. Mine looks a little bit different. There's like a typo I haven't fixed yet, but this is like the not final copy. So for y'all, it's answer choice D, which is 1.922. Alright, 23. 0.743 kilograms of CaOH2 is added to a solution. The resulting solution's volume is 1.52 liters with a density of 12.4 grams per milliliter. what is the mass percent of CaOH2 in the solution? Okay, mass percent. Mass percent. All it is mass of component divided by total mass. Okay, so they gave us a mass of a component, right, which was 0.743 kilograms. I think it's going to be easier just to go ahead and change that to grams. Just look at the other thing, because we have a density of grams, so we'll go ahead and change that to grams. So it's 743 grams. And now we have to divide it by its total mass. They don't give us a total mass, but they give us a volume of 1.52 liters and a density of 12.4 grams per milliliter. So I can change that to 1,520 milliliters and now I'll times that by its density, which is 12.4 grams per 1 milliliter. And let's see, 1,520 times 12.4. Yep. 18,848. So the mass percent is going to be 743 divided by 18,848. And I get 0.039, times that by 100%. You get about 3.9%. It's like 3.94, I think. Yeah, you can see it. But alright, so that's answer choice A, which is the correct answer. Moving on, 24. Which of the following is a strong acid? Strong acids, you just need to know. Sorry. But we can go through, and so acetic acid, that's not a strong acid. Nitrous acid is not a strong acid. Hydrofluoric acid, contrary to popular belief, especially shows like Breaking Bad was saying, oh yeah, hydrofluoric acid is like the strongest acid. It's not. It's a weak acid. And sulfuric acid is a strong acid, so that's answer choice D. Alright, 25. Which of the following will cause the reaction to shift to the left? A plus B yields, and this is the reaction, yields Ba plus C. And we had a delta H of negative X, so some negative value. We have decreasing the temperature. We have adding more A. We have removing some A, or we have adding more BC. Okay, the way I taught my engineers this, when you're talking about shifting reactions in which direction, let's think of it like a teeter-totter. So, teeter-totter, right? Or seesaw, or whatever the crap y'all call it. I call it a teeter-totter. So, we're going to take this teeter-totter, right? And so one side is going to be reactants. So A plus B, C. And the other side is going to be the products. BA plus C. Okay. So if we're looking at just this right here, we have A plus BC and then yields BA plus C. So A plus BC is on the left side, BA plus C is on the right side. So if we were to add, let's see, if we're going to add some more A, this side's going to get heavier, right? And so the seesaw will look like this. So what direction does it need to shift to balance out the seesaw? You would have to shift to this direction, right? To balance it out. So hopefully that makes sense to y'all. So now we have removing some A. So if we removed A, or took away a good bit of it, we're making the left side lighter, right? So left side would get up in the air like that, because basically teeter-totter, right? And everything would have to shift towards the left side. So the correct answer is removing some A. If you add BC, it's going to be the same thing that we did in the first one. This side will get heavier. It's going to have to shift to this side to counterbalance. Decreasing the temperature. When there's a negative delta H value, you can think of it as temperature being in the product. And so if we added more temperature, or excuse me, yeah, if we decrease the temperature, right, it'd be like decreasing the stuff on this side. And so it would cause this side to get lighter again, and things would shift to it. But you probably won't see temperature very much. But anywho, so yeah, answer is C. Alright, halfway done. So 26, which pH represents the strongest acid? You guys should know this pH, the stronger the acid, the lower the pH. So we can take a look and just see what number is lower. 1.2 is the lowest. So it is the strongest acid up there. An examination of a large compound revealed that it is mostly composed of hydrocarbons and features at least one C double bonded to C. This compound is most likely A or an AN. Strong electrolyte. That doesn't make any sense. Unsaturated fatty acid. Okay, we'll hold that one off for a second. Saturated fatty acid. We'll hold that one off for a second. An essential fatty acid. There's nothing in here that tells me that it's an essential fatty acid. So I can cross that out. I know it's going to be a fatty acid, but they would say, oh yeah, that you don't absorb naturally in your body. So it can't be that. So we have unsaturated fatty acid and saturated fatty acid. So if there's a double bond, it's unsaturated. So it works like this, right? So I'll just draw a little thing. But if there's a double bond, you could add more hydrogens across that double bond, right? And make it disappear. So if you can add more hydrogens to it, it's unsaturated. If it's just that and there is no double bond, it means it's saturated with hydrogens. It can't hold any more hydrogens. So in this case, since it has a double bond, it's an unsaturated fatty acid. Alright, in the following reaction, what happens to the carbon in the process of the reaction? Now, that seems a little redundant, but whatever. Fe2O3 plus carbon monoxide yields 2 irons plus carbon dioxide. Okay, we're looking at the carbon here. So this is going to be, well, I'll read the answer choices first to set me up for answering this. The carbon is oxidized. The carbon is acting as an acid. Okay. The carbon is reduced. The carbon is acting as a base. Alright, that was weird. Anyway, it's definitely not going to be B or D. We're not looking at those. We're looking at oxidation and reduction, right? So, remember, oxidation is the loss of electrons, reduction is a gain of electrons. So, let's take a peek here. So, CO, right? That means that carbon, since it doesn't have like a net charge at all, either carbon has to have, or most likely, has a positive 2 charge here, which is weird, and oxygen will be a negative 2. That was like their little oxidation numbers, right? So, in the next one, carbon's actually holding more. So carbon is now CO2, right? So total, this O2 is negative 4. Each one of these oxygens is minus 2, by the way. Hopefully you guys remember that little trend on the periodic table that starting at fluorine's little column going down, it'd be, you know, that column is negative 3, oxygen's column's negative 2, nitrogen is negative 1, carbon's plus 4, minus 4, boron is plus 3, beryllium, excuse me, so Be, that column going down, that is plus 2, and then the one with sodium in it, so lithium's column is plus 1. So oxygen total is minus 4 here. that means carbon has to go from a +2 to a +4. So if it becomes more positive, it loses electrons, right? So that's oxidation. Oxidation is loss of electrons. And remember, it goes from a +2 to a +4, so it loses electrons to become more positive. So hopefully that helps people out. Alright, so it is oxidized. Carbon is oxidized. 29, what type of reaction is being displayed here? You can tell we've moved into the 1152 stuff, which is nice. So we have a C dual bond C plus H2 yields, C2H6. Okay. So it's just adding hydrogen across the double bond. So that's hydrogenation. So hopefully you guys remember that. But remember, hydration is like adding a water. Halogenation, which is initial choice C, is adding a halogen, like chlorine, bromine, iodide, fluorine, stuff like that. And then hydrolysis is taking away water. So yeah, this is hydrogenation, which is answer choice B. 30. What does the ketone in the following reaction undergo? So, sorry, I'm just looking at something really quick. My friend's getting married in a couple days, and she posted like a really funny post on Facebook. It's pretty funny. Anyway, back to the matter at hand. Sorry, got distracted. What does the ketone in the following reaction undergo? So, we have inorganic reduction, organic reduction, inorganic oxidation, or organic oxidation. So, inorganic reduction, right? That's what we were just looking at up here. That's adding electron. Right, adding electron. Inorganic oxidation, removing electron. I'll just put E-. Organic reduction is adding hydrogen. Organic oxidation, removing hydrogen. / adding oxygen. Okay, so if we look at the oxygen here, the ketone, right? We're looking and we see that the oxygen in the ketone goes from a regular oxygen to now an OH. So it gets reduced because we're adding hydrogen to it. So that would be answer choice B. So it's organic reduction, by the way. The following structure is and we have this huge structure of like a bunch of monosaccharides hooked together. So let's see how many we got. 1, 2, 3, 4, 5, 6, 7 of them hooked together. So we have a monosaccharide, a disaccharide, and a oligosaccharide or a polysaccharide. Monosaccharide is just one, and there's definitely more than one, so it's not that. Disaccharide is 2, definitely more than 2. Oligosaccharide is like 3 to 9, normally, about that. Polysaccharide is like 10 plus, pretty much. So if we see it's 7, it clearly falls into oligosaccharide. So that's C. Alright, we're making good time, folks. Alright, moving on. 32. The following structure is which of the following? L-fructose, D-fructose, L-glucose, or D-glucose? Alright, so first off, is it fructose or glucose? Well, let's count the carbons. A big key factor here is fructose has 5 carbons. in its main structure. So let's see, we got 1, 2, 3, 4, 5, 6. 6 carbons overall, right? So not fructose. I can go ahead and cross those out. Now we're looking for L or D glucose. So we can see that the OH group here is on the right. If you guys remember that, if the OH near that carbonyl, right? If it's on the left, is left. That's an L. Is right equals D. So since it's on the right, it's a D glucose molecule. A blank bond connects two monosaccharides to one another through a condensation reaction. We have glucosidic bond, which that sounds really funny. I think they're trying to trick you here. Alkyl, hydrogen bond, or a glycosidic bond. Hopefully you guys remember this. This is just definition stuff. It's a glycosidic bond. So, alright, which one of the following is not a component of the fluid mosaic model? Cholesterol, lysozyme, phospholipids, or glycolipids. Now, this one's a little bit tougher. We know all about the fluid mosaic model, but we didn't talk about it like super duper in depth. So, what we did know is that fluid mosaic model, right? It's these phospholipids, which I know it's hard to see, but they're all hooked together like this to form this membrane. And in this membrane, right, cholesterol is there to help stabilize it. So we know phospholipid and cholesterol's in there. And there's also glycolipids in there acting in the membrane. So they help out as well. A lysozyme, though, is not. That's something else. I can't remember what that was. But yeah, it's not part of the fluid mosaic model. So yeah. Answer choice B is the right answer. A red blood cell has a salt concentration of 0.3%. What will happen if the cell is placed into a 0.1% salt solution? The cell will shrink, the cell will swell, the cell will remain the same size, or salt will enter the cell. Okay. Where's a clean piece of paper? Okay. So, I'll draw what we got here. We got a cell that's 0.3% salt. So I'm going to draw it like this. 1, 2, 3. 3 salts, right? And it's in a solution. That's what all this nonsense is. That is this is like the actual picture, and this is my diagram. 0.1% salt solution. Okay. So what's going to happen is water is going to flow from the outside in to the cell because it's semi-permeable membrane. It's going to flow into it, right, to try to quench these salts. So it wants to quench these. So water is going to flow into the cell and swell it up. Now the thing about these cells, though, is it is a semi-permeable membrane. So water can flow in just fine. The thing that can't is salt. Salt can't enter the cell. And there's no reason it would anyway. Salt can't leave the cell either. So, answer choice D is wrong. Cell will remain the same size. It looks like water's flowing in there to me. So, that's going to swell it up. The cell will shrink. No, that's if there was more salt on the outside. The cell will swell, which is answer choice B. Alright. Which of the following is not a type of passive transport? Remember what passive transport was? It's excuse me. It's a type of transport for all sorts of stuff. It doesn't require energy. Diffusion is this. Diffusion is just stuff flowing from a high concentration to a low concentration. Osmosis is what we just talked about here. Easy stuff. Facilitated diffusion, it uses, I guess transports would be the best way, but they still don't require ATP. It's stuff that's like channels, stuff like that. It doesn't require energy though. That's the main thing you need to know. Active transport does. That's a The example we talked about was a sodium-potassium pump, where stuff is actively pumped into the cell and out of the cell, you know, pumped, yeah, anywho. So we can take a look here. We have diffusion, osmosis, and facilitated diffusion. And those are all passive. And endocytosis, I have no idea what that is. I just know it's not passive. So that's going to be C. Alright. 37, moving on. Calculate the pH of a solution composed of a 0.051 molar H3O plus. Okay. So, H3O plus, you can basically treat it as just H. They're basically the same thing. H3O plus is hydronium, but a lot of people just look at it as this, H plus. It's the same thing, so they'll probably put H3O plus in your test somewhere to try to trick you, but it's just the same as H plus. So if we had to calculate the pH of a solution composed of 0.051 molar H, what is it? So all we have to do is negative log concentration of H, right? So it's going to be negative log of 0.051. I have a feeling it's going to be relatively low, probably 1. Let me see. 0.051. We're going to have log negative. Yeah, it comes out to be 1.29, blah, 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 keep going on. So, that's answer choice A. Alright. 38. A chemist wants to develop a buffer for one of her reactions. What should the chemist mix together to make the desired buffer? A weak acid and its conjugate base, an enzyme and a strong amino acid, a strong acid and its strong base, any weak base in a molecule at its isoelectric point. So, I'm going to review a couple things in this question, just to make sure you guys are set. But, first off, isoelectric point brings up something we haven't talked about in a long time, Zwitter ions. Zwitter ion, right, we'll have, what would be a good way to represent it? I'll just put a box. So Zwitter ion is this. We'll have a box with a negative charge. We'll have a box with a positive charge and a negative charge. And we have a box with just a positive charge. Okay. So these are going to be your amino acid or whatever you're looking at, these boxes are. So a Zwitter ion is this middle one, where it's got a negative charge and a positive charge, but they balance out to each other. That point at which a Zwitter ion occurs is the isoelectric point. So if this occurs at pH, I don't know, 7.3, that would be the isoelectric point. So anyway, that's Zwitter ions for you. Easy little, not too in-depth, but I don't want to go too in-depth. There's a lot of stuff on this test. So anyway, but that's not the answer or anything. I just wanted to go over it for you guys. A buffer, just so you guys know, this is almost a straight definition if you know what it was. It's a weak acid and conjugate base. So weak acid and conjugate base. That's what a buffer is. And we can actually see that's answer choice A. So, not too bad. Easy stuff, right? So, buffers, if you guys don't know what they did, they compensate for pH changes. So, a solution, let's say you normally add some acid, right? And it goes from like a pH of 7 to like a pH of 1. If you added a buffer, right, what happens is these conjugate bases and weak acids work together, and so it's going to, instead of dropping the pH down like a ton, it's going to drop it down just a small amount. It's going to go from like 7 down to like 6.9 something, which is relatively small compared to 7 down to freaking like 2. Okay, 39, an alpha helix is an example of blank structure. Primary, secondary, tertiary, quaternary. Primary structure is just the sequence. Secondary structure is what we're looking at here. Secondary structure is an alpha helix, beta sheets, that type of stuff. It's a little bit more complex. So that is answer choice B. So an alpha helix is answer choice B. Alright, number 40, an inhibitor is observed to not resemble a substrate and causes a conformational change in an enzyme. What type of inhibition is this? Nuclear inhibition, competitive inhibition, non-competitive inhibition, or irreversible inhibition? Okay, so the types of inhibition here. Nuclear inhibition, first off, that I don't even think that's a thing. But so we have competitive. So let me draw an enzyme. So that's my enzyme, right? Right, enzyme. So that's my enzyme. So and here's the substrate that normally goes into this box. I'll just put S for substrate on it. Normally, a competitive inhibitor, so competitive inhibition, you have something that looks almost identical. Almost. So we'll have like a little something coming off. Almost identical to the substrate. I'll put I for inhibitor. And it just looks identical to it. And so it just binds right into this binding pocket and just keeps clogging up pockets because there's so many of them and they look exactly like the substrate. The enzyme gets them confused and it starts just working with those and nothing happens. The next type, which let me draw another one, is non-competitive inhibition. So we have our normal substrate right here, right? And then we have a non-competitive inhibition. We have something that's like, looks totally weird. Let's say it's like, yeah, okay, that. So it binds somewhere else on the enzyme, and it causes the enzyme to change shape. So instead of a binding pocket of being like square, it's now like a circle or something, and you have to fit this binding pocket now. And so of course this thing won't fit in there anymore and it just stops binding. A irreversible inhibitor, and let me put this, so competitive, non-competitive, and the last one, we'll have our enzyme again. A irreversible inhibitor is when you have something like this that just comes in and it's like a bar. It just bars over the binding pocket. So the binding pocket is not usable anymore. It can't, the substrate can't get into it because it's like physically blocked. It's not that, oh, it caused a conformational change. It's physically blocked. And that's normally irreversible. Oof, butchered that. Okay, don't read that spelling, it's horrible. So, in this case, it says, it does not resemble the substrate, so that narrows it down to non-competitive and irreversible. And it causes a conformational change in the enzyme, so that would make it non-competitive. That's when it binds somewhere else here, and it changes the shape of the binding pocket. So that's non-competitive inhibition, which is answer choice C. Okay, one part of the genome that encodes for a particular protein is a what? Ribosome, lysosome, chromosome, or gene. That's the definition of a gene. A gene is, it's part of the genome that encodes for a particular protein. So, answer choice D. Alright, all of these nitrogenous bases are found in RNA except which of the following? Adenine, thymine, guanine, or uracil. So, this is RNA. This is RNA, remember? So, RNA the nitrogen spaces that make it up are A, G, C, and U. So if we look through adenine, that's part of it. So we're looking for one is not a part of it. Thymine is not. Sometimes it might get in there, but that's a horrible mistake. So thymine definitely not supposed to be a part of RNA. So on to the last page. Alright. What genetic sequence would be found in the mRNA resulting from the following DNA sense sequence? Of 5', let me flip this, write this down. 5' A T T A G C A 3'. Okay, so that's the DNA sense strand. Okay, so there's a couple ways we can go about this. You can go the long way and go DNA sense to antisense and then antisense to mRNA. And so I'll show you that one. That's the long way if you can't remember this little trick. So DNA sense, I'll do this to antisense. And so we take these and we're just going to flip them. So this right here, this guy turns to T, A, T, C, G, T. Alright, so that's the antisense. And you can scoot one more down to mRNA. And so mRNA would be this flipped right here, so 5', except instead of T's, it's now U's. So that's going to be 5' A, U, U, A, G, C, A, 3'. And so the little trick, you can either go the long way if you can't remember, but the trick is that to go from a DNA sense strand to an mRNA strand, if you want to save time, you can literally just change the T's to U's. And that's your answer. So that's a little trick, might save you some time if you need it. So let's look for A, U, U, A, G, C, A. Yep. So answer choice D. Alrighty. 44. What amino acid sequence would result from the following mRNA sequence? Okay, for this, you'll have to use a codon table, which they give you on the front page of your exam. I know they're going to give it to you. If not, something's up. But, so let's break it into codons, right? So codons are 3 nucleotides. So let me put that there so I don't get you guys confused. So UAU is the first one. UGU is the second codon. GAC is the third codon. And CGU is the fourth codon. So we can look in our codon table. UAU is tyrosine. And then, what's next? UGA, right? Yeah, UGA. Where's that? Oh, not UGA. That's a stop codon. It's UGU, excuse me. What's this? Cysteine. Man, that would have been weird. It was like instantly stopped. GAC. Alright, let's see where that is. GAC. ASP, and then CGU. So CGU, arginine. Alright, so let's take a look. That appears to be answer choice A. The other ones, even C, we just worked it out. The other ones aren't close. Okay, a retrovirus is different than most other viruses because retroviruses undergo transcription, recombination, reverse transcription, or silent mutations. Okay, I'm going to go over a couple things here. So transcription, everything has transcription to it. So, yeah, that's going to be there. Recombination, pretty much everything undergoes recombination. I don't really think we talked about recombination very much, so I wouldn't really worry about recombination. Reverse transcription is the process of taking RNA and bringing it up to DNA. It doesn't normally happen in that, using an enzyme called reverse transcriptase. Alright, so, and then a silent mutation. Okay, mutation is a change in a DNA sequence, right? Like this right here. A silent mutation is a change in that sequence, but it doesn't result in a new phenotype, which that just means it doesn't make it really any different. So an example of that would be, see how this is like CGU at the end here, and that codes for arginine. If it changed to CGC, which also codes for arginine, that would be a silent mutation. So, but in this case, the answer is reverse transcription. That's just the thing about retroviruses that's very specific to them, is they're RNA based. They get into a host and then they convert back to DNA. They mutate a lot. Just so you know, that's why they're so hard to cure. But common colds, I thought, a retrovirus. But anyway, yeah, let's see. Alright, moving on to 46. All are examples of catabolism except which of the following. You guys probably saw a question similar to this on one of my practice tests. So I pulled something very, very close to it. 46. All are examples of catabolism except which of the following. Glycolysis, the breakdown of muscle protein, the citric acid cycle, or photosynthesis. We have to know what catabolism is, first off. Catabolism is the breakdown of something. Breakdown for energy. So it's breakdown for energy, right? So we can look at this. So one of them even says the breakdown of muscle protein. Yeah, that's going to be catabolism. Glycolysis. Not many people think of it as catabolism, but it is. You're taking the glucose and you break it into pyruvate, so you're breaking it down, and it produces a little bit of energy. So it's catabolism. Citric acid cycle, you're breaking stuff down like the whole time. That's catabolism. And then you're making a ton of NADH, which is used for energy. And photosynthesis is the only thing. It's actually the building up of stuff. So that's answer choice D is the correct answer. You don't really break anything down in photosynthesis very much. Okay, 47. This is like the last stuff we covered in class. So 47, 6 glucose. Excuse me. 6 glucose molecules subject to glycolysis will yield how many NADH molecules? Okay, this is just knowing glycolysis. So as long as you know each glucose molecule yields 2 NADH. We can go through, you got 6 of them, so 6 times 2 gives you 12. So it makes 12 NADH total. So that's going to be answer choice B. Alright, 48. 2 glucose molecules are run all the way through the citric acid cycle. How many NADH molecules are formed? Okay, it's run all the way through the citric acid cycle, right? So, excuse me. Dang. I think I'm getting allergies. They're just killing me right now. Okay, anyway, so 2 glucose molecules. I'll get a new piece of paper. So 2 glucose molecules run all the way through the citric acid cycle. How many NADH molecules are made? Okay, so we're starting with glucose. So glycolysis breaks it into 2-pyruvate. And makes 2 NADH, and also 2 ATP, but we're looking at NADH here. Okay, then there's that intermediate step of taking the 2 pyruvates, right, and converting it to acetyl-CoA, and that produces an NaOH for each of them. So 2 NaOH and NADH, excuse me, for each of them. And then citric acid cycle. So I'll just put CAC for citric acid cycle. That produces 3 NADH for each acetyl-CoA that comes in. So there's going to be 2 runs of the citric acid cycle. It's going to make 6 NADH. Okay, so each glucose molecule run all the way through citric acid cycle. It makes 10 NADH. I don't know why I wrote that as small a, NADH. So each glucose molecule run all the way through the citric acid cycle makes 10 NADH per glucose. So let's take a peek here. They said we have 2 glucose molecules, so it's going to be 10 times 2, which is 20. It's going to make 20 NADH. Alright. In cellular respiration, which process generates the most net ATP? Okay, so cellular respiration, for the most part, it's glycolysis, going to citric acid cycle with that weird intermediate step, but that's not like super huge, but it's very important, but these are the main things. Glycolysis to citric acid cycle to electron transport chain. And the best way to think about it is glycolysis, prep, for prep, citric acid cycle, final prep, electron transport chain, where the magic happens. Okay, where the magic happens. Electron transport chain, it basically takes all of the NADH and FADH2, right? And it converts it to ATP. So, just so you know, if you did have to calculate it, every NADH that you have, God, where is it small again? Let me pull this up so you can see it. Every NADH that you have, it gets oxidized. So, produces 2.5 ATP. And for every FADH2 you have, it produces 1.5 ATP. Okay. Total each run from glycolysis all the way through electron transport chain, normally, and that's normally, it's around here, makes about 32 ATP. About. Like I said, it's not totally efficient. Some people produce less, but pretty much 32 ATP. So 49, again, in cellular respiration, which process generates the most net ATP? That's going to be electron transport chain, because it converts all the NADH to FADH2, NADH to ATP, and FADH2 to ATP. So you end up with a ton of ATP after electron transport chain. So it's electron transport chain. And then 50, 2 glucose molecules undergo the entire process of cellular respiration. How much net ATP is produced from this process? Well, luckily we just talked about this. We said that 32 ATP is produced per run of cellular respiration. So per 1 glucose run of cellular respiration. So that means we take that, times it by 2, should be about 64, give or take. And so we look 32 is an answer, so that's for 1. 6, I don't know what that is. 64, that's the correct answer. And then 128 is way off. It's double that. That'd be 4 glucose. So we'll circle answer choice C is the correct answer. So that goes all the way through it. If you guys have any questions, please email me. And if I don't see you, I should be at the final helping proctor, but if I don't see you guys, I hope you have a wonderful summer and get some downtime, relax, have fun, and it's been fun having you guys. So thanks so much. Hope you guys have a good summer, and I'll talk to you later. Bye.